when the ray travels normal to the interface. It'll go straight down, right? This angle will basically be theta 1 will equal 0. So sine theta 1 over V1 equals sine theta 2 over V2, which will equal 0. So the ray will go straight down. The other thing that occurs at normal incidence is that there is no conversion from P to S or vice versa. So there's only, at normal incidence, there's only going to be 3 waves. There's going to be the incident P, there's going to be the reflected P, and there's going to be the transmitted P. If we're talking about a vertical shear wave, there's going to be an incident shear, a reflected shear, and a transmitted shear. There will not be an S if it's just an incident P. There's no conversion at normal incidence. If there's just an incident S, then there's no P. Okay, so this problem gets a lot simpler if we simply worry about normal incidence reflection. We don't have to worry about conversion, and we don't have to worry about refraction. And this is really the simplifications that are used in reflection seismology, which we'll go into a little bit later on, as opposed to refraction seismology. In refraction seismology, we're trying to generate waves at an angle to interfaces so that we can generate those head waves, the refracted waves that travel along. In reflection seismology, typically we're more interested in avoiding the complications associated with these conversions that take place at interfaces. So the first order, and we'll talk about as it gets more complicated, we actually like it, but the first order, we want to keep it close to normal. Okay. So let's now go to our travel time curves. All right. So we did this last time, but I want to go again in excruciating detail through this because it's going to be critical again to most of the work that you're going to be doing from now on. So I get a hammer blow, I've got a series of geophones, and I have travel time versus horizontal distance, all right? And those are little dots, okay? Those dots, what are they? Would you call those a seismogram, or would you call those a pick of a seismogram? What? Pick, right? The dots are a single travel time associated with the direct wave. And so we can describe the direct wave as simply a line in this time distance space, where the line, the slope of the line, is the velocity of the wave as it propagates across the geophones. Now, just for grins, suppose I had a hammer blow here, and I sent a wave deep, deep, deep into the earth that reflected and came up vertically to all the geophones at a particular time. And I picked that time. What would I see? So let's do that exercise here. So let's look at this particular geometry. We've got a hammer blow, and it sends a wave way down in the earth, and the wave comes back nearly vertical, maybe a little bit of an angle, but basically the wave comes back like this. So the ray path is almost straight down and straight up. Okay? And I've got all my geophones along here. What will I see in this time distance plot? So x and time. What will the time curve look like? Time fixed for each of the geometries. Do that as an exercise. What will the slope? Will it look like this? Will it look like this? And will it look like this? What will the slope of that fix? What will the intercept? Can you figure out what that will be? The wave's coming straight up, right? So what's the slope? Right? High positive slope. So, okay, that's good. That is very helpful. All right. So you think that it'll look like this? Yeah, right? Good. So what's true about the travel time difference between, if the wave is coming straight up, and both these ray paths are about the same. If the ray path length doesn't change from offset to offset very much, what has to be true about the travel time? It's flat. It doesn't change. The wave is coming straight up. So this time, if this is the time of the reflection, then this reflection time is that plus a little bit of additional time. Not much. And then maybe this is TR plus 2 epsilon. But basically, if you make epsilon small enough, there's not going to be any travel time change because these rays are coming dead straight up, really straight up. And the way we get that to happen is to have the reflection super deep. And the rays have to come straight up. This distance relative to the depth of the reflection is going to be extremely small. So, what we get is we actually get a straight line, maybe a little bit of a slope, and this is at TR. So notice this, that at that slope, it's much flatter than the direct way. What do you think happens at intermediate angles? Suppose there's a reflection that comes from here at some intermediate angle. Or let's say that there's a wave that's coming in to this array at some intermediate angle. What will the slope look like? So if the wave is coming as a direct wave dead horizontal, then we know that the slope